Yes, I can see the slide, maybe.
Okay, very good. Thank you. Just tell me when you are ready to get started.
Yes, just a moment.
And I will have to apologize in advance. I was notified yesterday that there's a chance that there might be construction happening anytime. So if they start cutting the concrete slab, I think I will have to flee my office. So this will make for a much more interesting meeting, because then you'll see part of the physics department here at CU Boulder. But my hope is still that this does not happen, and I will be able to finish the seminar without any concrete slab cutting in the background.
Okay, no problem. So we can begin. So I am not able to see your slide. I can see your screen. So
Oh, okay, good. Then let's try this again. Zoom always makes for interesting. Can you see this now?
yes, now I can see. So welcome everybody to the last talk of the day by Paul Romatschke from Colorado University Boulder, and he's going to talk about mass generation and asymptotic freedom for large N abelian Higgs model. And maybe I'll send you a reminder when 5 minutes are left.
Yes, thank you. Okay, yeah, thank you. Good morning, good afternoon, good evening to every one of you in the different time zones. I will be talking about this sort of very broad topic, but really sort of the plan for my talk is sort of shown in the next slide here. So I want to sort of advertise large N expansion techniques for quantum field theory. These are not really new techniques, but we have made some technical advantages or adjustments in the last few years, which I think make these old large N expansions a very, very powerful mathematical technique to actually solve quantum field theories, most notably scalar quantum field theories. And I want to sort of first tell you about the method, because it's very broadly applicable, before I then sort of go to the application to physics. In particular, I want to talk about scalar fields in 4 dimensions, before I then will give a very concrete model, namely an abelian Higgs model, that can be solved non-perturbatively using these large N techniques. And hopefully this should make for some interesting results. I don't really have an agenda for this talk, so if there are any questions that you might have, please interrupt me. I will be sort of trying to answer your question as much as possible, but if I only get through half of my talk, that's perfectly fine with me. Okay, to get started, I want to talk about large N expansions, and most likely if we have not worked with these, the few slides that I have on this topic will be too brief to really sort of give a good understanding of what's going on. So that's why I highlight this reference here. This is an archive preprint. These are lecture notes for lectures I gave at the Krakow School in Theoretical Physics in Zakopane last year. And they have a lot of detail that I will not be able to cover in these seminar today. They also have homework problems. So really I think it's a useful way to really get familiar with this technique, which is very different both calculationally and conceptually than usual perturbative quantum field theory. Okay, so let me jump right in. Let's talk about the quantum field theory. And the quantum field theory example I'm going to talk about is the so-called ON model. So it's N scalar fields, N component scalar fields lumped together into a vector, phi vector. And then the standard object I'm going to talk about is the partition function Z, which is given as the Euclidean path integral with the action SE that I've denoted here. So it's a standard quantum field theory. There's a typical kinetic term here, and then there is a potential term. I've used a quartic potential here. And the only thing that might be slightly unfamiliar is that the coupling here is entering in the form lambda over n. You might think that, okay, this means that this coupling diminishes in the n large N limit, but the N scaling is such that if phi is an N component vector, then phi squared is N times the number of or N times the scalar squared. So if you square this, you get an N squared, and that is why there has to be a normalization 1 over N here, such that this model actually has a good large N limit. Okay, so this is the model. It's known as the ON model in particular the condensed matter literature. It corresponds to a field theory in these space-time dimensions. Okay, so I didn't write down here, I hope you can see my mouse, I didn't write down here the dimensions of this integral over space-time x, but this theory can be formulated in these space-time dimensions, and pretty much anything I say is general about D, so it applies to any D that you want to apply it to. I want to give some examples of what this field theory actually corresponds to. So if you do these one, so this is 0 plus 1 dimensional quantum field theory, also known as quantum mechanics, then this theory here describes a point particle in n spatial dimensions. Okay, so it's a point particle in n spatial dimensions with a quartic potential. And you can solve the Schrödinger equation for this, which is a different method, or you can sort of see it in terms of this field theory, that the same sort of setup, which provides one way of actually testing whatever large N expansion techniques you might have. Another example that I want to highlight is that in 3 dimensions, so 2 plus 1, this theory has a conjectural gravity dual, in particular Vasiliev gravity in asymptotic ADS4, which was outlined by a very nice paper by Klebanov and Polyakov about 20 years ago. In the case of 4 dimensions, so this is 3 plus 1 dimensions, if you specify the number of scalar components to be 4, this is nothing else but the standard model Higgs case, because in the standard model, the Higgs is a 2-component complex scalar, so that is total of 4 real components, which maps to this theory in the limit of n is 4. So I wanted to sort of point this out because this basically sort of says that this model has direct physical examples that people care about. So it's not just a completely sort of academic exercise to want to sort of know something about this property of this model. Now let me talk about the solution techniques for the ON model. There's clearly a possibility that you can use weak-coupling perturbation theory. So you do an expansion in lambda much less than 1 and sort of use Feynman diagrams to sort of build up the theory. This is a well-motivated method. It's conventional and it's extremely well studied. However, because it's perturbation theory, it only gives access to region of small coupling, so basically around the point lambda is 0. And the reason is actually interesting. It's not just because you expand around this point, it's also that the theory has a branch point at this location, which means that the radius of convergence of perturbation theory is 0. Okay? So it's an asymptotic series. You can't really sort of give, at least unless you have some example where for some reason you have an extremely large number of orders where you can do Borel-Lewis summations, you typically cannot sort of explore the phase diagram except around the point lambda is 0. And if you want to sort of apply this weak coupling perturbation theory to quantities of interest that are, let's say, of coupling of order 1, then oftentimes perturbation theory gives rather poor quantitative performances. And you might have known this in perturbation theory when sort of orders sort of start flipping around and sort of behaving strangely. That's typically what you encounter with perturbation theory when you sort of apply it, if you want to, outside of its regime of applicability, which is really lambda is 0. Only the free theory is where it sort of is good. I want to contrast this with the large N expansion techniques. So similar to the weak coupling perturbation theory, where you take lambda pitch much less than 1, you have a small expansion parameter. In a large N expansion, you take n to be extremely large. So 1 over n is a small parameter, and you can use this parameter to systematically expand the quantum field theory. Again, this is very well motivated, but it's rather unconventional since most of our quantum field theory textbooks use perturbation theory, and very few of them only use large N techniques. So there are comparatively few studies in the large N technique method. What is something that I want to highlight in this talk is that contrary to perturbation theory, the large N expansion techniques often give surprisingly good quantitative results, even down to n is 1. And this is not something I can really sort of explain very well. It's just that there's sort of evidence that you sort of look at sort of quantities in the large N expansion, and for some reason it works extremely well around n is 1. You might have encountered these kind of surprisingly good large N features in the context of young mill theories, where you do lattice studies for large N young mills, and you find that the large N result is actually sort of more or less on top of N is 3, which is a case we care about. But of course, there the difference is that the large N young mills results, they don't really sort of lend themselves to solution techniques using large N. You still have to use non-perturbative lattice studies to do this. Whereas for scalar and fermionic theories, large N really lets you solve the theory, which is what I want to highlight in the next few slides. Okay, I wanted to sort of take the moment or take the opportunity to walk you through these large N solution techniques in 3 slides. Okay? So how does it work out? The reason that we need to sort of even talk about large N expansion techniques is the fact that the Lagrangian that I've written down here has a quartic term. Okay, so there's a phi squared squared term. And because we can only do Gaussian integrals and the path integrals exactly, we can't do quartic terms. So we have to sort of do something with this quartic term in order to sort of solve the theory. What you can do, and what is well known in the condensed matter literature, is the so-called Hubbard-Stratontovich transformation, which is an exact mathematical identity that lets you rewrite any quartic interaction term, let's say I have an example with just e to the minus lambda x4 here, as an integral over another field, an auxiliary field, which I call zeta, and the action for the auxiliary field is no more than quadratic. Okay, so there's a zeta squared, and there's a Fourier transform term zeta x here. And you can check this out. This is an exact mathematical identity, and you can use it to reformulate the quantum field theory with any quartic term that you might encounter. This works in all theories because it's mathematical identity. So once you do this, once you rewrite the theory in terms of this auxiliary field, the effective Lagrangian that you get is written down in this line here. It is now quadratic in the fields phi. It's quadratic in the fields zeta. And there's one 3-point interaction where zeta couples to phi squared. Nevertheless, because the phi here sort of is quadratic, it can be at least formally integrated out. And what you end up with is this formulation of the action, where you still have the quadratic term of the auxiliary field, and you have the trace of an operator that depends on this auxiliary field. Okay? So I want to emphasize that this is not an approximation. This is a mathematical rewriting of the original theory in terms of new degrees of freedom, this zetas here. It's the same theory, just different variables. Okay, now that we have this, you might say, okay, this is a very complicated action. It's non-local because there's this operator. Do we really sort of have something that we gained? And the point here is that I want to draw your attention to the fact that both of these terms in the auxiliary field action scale as n. Okay, so that means that if n is very, very large, the partition function here, because there's an n in the exponent, can essentially be solved with saddle point methods. And the saddle point method is an approximation for any finite n, but it becomes exact in the large n limit. So the way this is sort of done is that this path integral becomes a sum over all possible saddles that the theory might have. And then it's the usual sort of result that you have the action evaluated. I think I pulled out the n here, so this should be the same action as before, over the determinant of the fluctuations. So again, in the large n limit, this result becomes exact. And the only thing that you have to sort of do is you have to sort of check and show that the actual saddles that you get are the ones that are given by the configurations where the field zeta of x is actually constant. So it's some constant zeta naught. So this requires some care, but this can be shown. So after this dust settles, you find that the large n approximation for the quantum field theory in any dimensions is given as a single integral d zeta naught over these saddles. And since the single integral over the saddles again has this structure of e to the minus n times something where n is very, very large, you can again use saddle point method to evaluate this remaining integral. And you find that the path integral, or the partition function for these quantum field theories all sort of become very simple. They're just given as the exponential of minus n times the action evaluated at the saddles. And again, this is general for all of these theories where you can do this Hubbard-Stratonovich transformation, and general for all dimensions. So the sort of really the meat of the theory is then contained in the saddle point solutions. So these solutions, zeta naught or zeta bar, as I call them here, that are solutions of the action having a saddle point. So the derivative of the action at that point is equal to 0. Oftentimes, this zeta bar here happens to be not on the real line. So this is why this is not sort of a minimum of the effective potential. But we have sort of, since about 20 years, a very good understanding of how to contour deform these path integrals away into the complex plane. And there's the so-called Lefschetz-Picard theorem that lets you sort of deal with the saddle points that are off the real axis. So z bar is a complex number, and this can be well defined through finding the thimble, calculating the intersection numbers. All of these things can be done, but are probably sort of too much for somebody who has not actually sort of worked with this. So I'll just mention this has to be done, but I say that, okay, at the end of the day, it really sort of boils down to just finding these zeta bars, which are solutions of this, and just plugging it in, it gives the same result. So most likely, if you have not worked with this, I suspect that you might have gotten lost in like these 3 very technical slides. And I wanted to emphasize that you don't have to worry. This happens frequently if you have not had experience in this. And again, sort of my reminder that if I at least could pique your interest, take a look at my lecture notes. There's sort of walk through examples of how this works out in practice, and also for sort of other theories such as multi-component fermions. Okay, so this is the technique. Let me now talk about some of the physics interpretations of what comes out of these techniques, because so far we have only been talking about math and not physics. So I talked about this rewriting of the original field theory in terms of this new auxiliary field zeta, which is a composite field. Here it's just a composite of the ON vector. Okay, so it's the singlet that you can build out of these vectors phi. Again, in different theories, for instance, for non-realistic fermions with 4-point interaction, you can do exactly the same thing. And the interesting thing there is that zeta is a boson, whereas the original fields were fermions. The same technique goes through. The thing that I want to emphasize is that for non-relativistic fermions, we know what the zeta is. Okay? The zeta is nothing else but the so-called Cooper pair that you might have heard in the context of BCS superconductivity theory. BCS sort of used some guess, if you want to sort of guess that this was the case, but here the Cooper pair just pops out from this mathematical rewriting of the original field theory, and you don't have to sort of assume anything. It's just contained in the math, and the only thing that you need to do is to say that, oh, well, this is not a sort of fictitious particle. This is an actual field. It corresponds to the Cooper pair. And another thing that you find is that these saddles that I talked about, in particular the non-vanishing saddle, is nothing else but the gap parameter that you have in superconductivity theory. So at least in the case of fermions, this auxiliary field is more than just a mathematical trick. It has real physical meaning, and I would advocate that we attach the same kind of physics interpretation to this auxiliary field zeta in other field theories, such as the scalar field theory. So one thing that you can immediately find is that this zeta bar is usually the global zero mode. I told you that it's a constant. It's a global zero mode constant. And there is sort of a notion that something like this should happen in scalar field theories. There's some articles by Paolo Sea where he sort of says that he expects there to be a Bose-Einstein condensate in scalar field theories in 4 dimensions. And in this case, where we sort of do the math, we do find there is to be this global zero mode, which does correspond to the Bose-Einstein condensates, at least for non-realistic fermions. So I think there's a pretty good sort of understanding that this auxiliary field might be just a mathematical manifestation of these physics concepts, which we sort of know and like. And again, sort of the fluctuations around this global zero mode, I would argue, are real physical excitations, so they can correspond to additional particle degrees of freedom, which are not contained in the original action. Now you might say, okay, this is some math, but how do we actually sort of know that the math is any good? Well, we need to check it. One way to check it is that we can compare whatever comes out of the solution techniques to other sort of results that we trust. And this can be done, but it can only be done in quantum field theories of dimension less than 4, because it happens to be that those are the cases where we have independent sort of methods which we trust, so that we can actually check how good the large N results really are. The simplest case is that of quantum mechanics in n dimensions. So again, take a point particle in a quartic potential and solve the Schrödinger equation, and then compare to the large N solution techniques with the saddles and so on and so forth. So again, in quantum mechanics, this would be the Hamiltonian. So it's in n dimensions. It has this quartic interaction term. And then if you solve the Schrödinger equation, you get results for the ground state energy, which, by the way, is the hardest observable to calculate. And in the 1 over n, well, you can sort of do this for different n. N is 1 is here under the right, n is 2, n is 3, 4 dimensions, 5 dimensions, and so on and so forth. And the dots are calculated from solving the Schrödinger equation, whereas the lines are the large N expansion, 2 different orders in the 1 over n expansion. The leading large N order is this black line here. The next to leading order is the dashed line. Then we have the dashed dotted line, and so on and so forth. And what you're sort of supposed to be looking at is that even the leading order large N result, which is sort of this line here, if you look at the scale, even for n is 1, it's off by only about 30%. Okay? If you sort of want to say, okay, 30% is not good enough, well, if you go to sort of either next to leading order in large N, or if you go down to n is 2, or up to n is 2, depending on your point of view, then you find that the large N expansion performs extremely well, quantitatively speaking. So it actually sort of works down to n of a few, maybe not 1, but a few. And that is sort of certainly something that people actually have used to sort of solve certain quantum mechanical problems using this large N expansion. So this for 1 dimensions, the large N method works quantitatively well. And I want to sort of emphasize that this is not obvious. And for those of you who don't believe me and say that, oh, this is guaranteed, it was clear that this would work out, I would suggest please calculate the ground state energy of this Hamiltonian for any n using perturbation theory. Good luck with that. Now, that was quantum mechanics. So you might say, okay, we are really interested in quantum field theory. Quantum mechanics is just too simple a test for this method to really sort of get confident that this method works. So let me jump to 3-dimensional quantum field theory, which is an example of a super renormalizable quantum field theory. And you can calculate something that is called the critical exponent, delta phi, for this ON model. And the nice thing is that there is results from the numerical bootstrap, again, for different n's. These are, again, these sort of black dots that I have shown here. N is 1, 2, 3, and so forth. And we also have large N expansion results, leading order up to N3 annul. And the point, again, to make is that if you look at the scale here, you find that the ON model works down to n of a few. You might be arguing whether this is 1 or 5, but it's not a million. And this is now an honest-to-God quantum field theory. Critical exponents are extremely hard to calculate using perturbation theory. So the large N method just passes this test with flying colors, even if this is a quantum field theory and not quantum mechanics. So what I want to take this as is a hint that this math, the large n expansion math, actually sort of works, at least in lower dimensions. So what I want to do now is take exactly the same mathematical method and just go to 4 dimensions. And the difference to in 4 dimensions with respect to lower dimensions is something I want to talk about because it's important. Again, most likely, if you have never heard this story, you might get lost in the mathematics. There's a reference that I want to point out here, which is a paper that I wrote entitled "What if phi-4 theory in 4 dimensions is non-trivial in the continuum?" And it has sort of lots of additional details to what I'll be able to do in this talk today. What I want to talk about 4 dimensions is the notion of quantum triviality. You probably have heard about this. If you open up Wikipedia, this is what you get. It says that if you take a scalar quantum field theory in 4 dimensions, if you renormalize the theory, or you have to renormalize the theory because it's 4-dimensional quantum field theory, then it turns out that in 4 dimensions, the theory in the continuum, the renormalized theory in the continuum, can only be non-interacting. So the effective running coupling at a scale that you care about has to be 0. So the theory is trivial because it's essentially free, and this notion is known as quantum triviality. Because this might be sort of slightly, because it's central to sort of the rest of my talk, I want to emphasize and sort of give an example of this so-called quantum triviality condition, which is that the running coupling evaluated at some scale that you care about is 0 in the continuum limit. So how does this come about in a nutshell? So let's think about the running coupling of 4-dimensional scalar field theory as a function of the running energy scale. Okay, so this is the running coupling as a function of the log of the energy scale. And for scalar field theory, you typically get a result that looks like this. Okay, so the running coupling increases. And then if you were to do this theory on a lattice, you would sort of have a lattice spacing or a UV scale at which you cut off sort of modes. This is the inverse lattice scaling spacing lambda. The inverse lattice spacing is lambda UV. And for your lattice theory, you would have to plug in a value for the lattice simulation lambda naught at this scale where you sort of simulate the theory. And of course, the running coupling sort of has to sort of match this point because that's what you're simulating on your lattice. But of course, this is not a continuum. This is a lattice theory with a lattice cutoff lambda UV. So what you want to do is you want to probe the theory in the so-called continuum limit. You want to make your lattice spacing smaller. And as you do that, increase the lambda UV. Before I go there, I want to point out that we are not interested in the value of the running coupling at the UV scale. We are interested in the value of the running coupling at some scale that we care about, let's say the Higgs mass or something. So now that we sort of increase our lambda UV scale by decreasing the lattice spacing, we again fix lambda naught to be some finite value at this new lattice scale. And then because the running coupling is still a running coupling, it has to match this point there. And basically what it means is that this black line shifts here to the right. And as a consequence, you find that at the scale that we care about, the effective coupling parameter lambda has decreased from its original value. Now, what you have to do in order to reach the continuum limit in your lattice theory is you have to repeat this process. You make your lattice spacing smaller and smaller, means that you push your lambda UV to higher and higher values. And as you can see from this sketch here, what you end up doing is you decrease the value of lambda at the scale that you want until when you reach the continuum limit, the only possible solution you can have is lambda is 0. So this is what quantum triviality really sort of means. The notion of quantum triviality is linked to the sign of the beta function. In particular, the notion that if the beta function is positive, then the running coupling has this positive slope. And that basically sort of, in this sort of lattice construction, implies that if you take the continuum limit, the running coupling at the scale that we care about has to go to 0. And this is quantum triviality, as I explained before. This is not something that is an ancient kind of thing that physicists sort of have dealt with and done with 50 years ago. Some people think that quantum triviality was proven 50 years ago. This is actually wrong. The proof of quantum triviality in 4 dimensions is only 5 years old. It's from these two gentlemen, Michael Eisenman and Hugo Duminil-Copin. And it's a big thing in the math community. You might know that Hugo Duminil-Copin got the Fields Medal 2022 for this proof. So it's a sort of recent sort of development in the math community, and it's really sort of something that sort of elicits a lot of sort of excitement. Let me sort of tell you from this point of view about a slightly, well, seemingly unrelated different sort of physics topics which comes up, which is the notion of asymptotic freedom. To talk about asymptotic freedom, I usually use this slide here from the CERN press release, where they try to infer the running coupling of QCD as a function of the energy scale here. So these are these dots here from the experiments. The line here shows the theory prediction from QCD. And the point is that the QCD coupling decreases as a function of energy. Okay. In RG speak, that means that the beta function is negative. So beta has the opposite sign of scalar quantum field theory. And this notion of negative beta function implies what is known as asymptotic freedom, which is simply the point that if you follow this line here all the way to extremely high or asymptotically high energies, the effective coupling is 0. So that means that there's essentially no interaction between the constituents, quarks and gluons. So we have an almost asymptotically free quantum field theory. Again, this is something that physicists care about quite a bit. There was a Nobel Prize associated with this to David Gross, David Politzer, and Frank Wilczek. And I wanted to highlight that David Gross, together with Sidney Coleman, looked at this in more detail. And in fact, they have an article out there entitled The Price of Asymptotic Freedom, where they point out that only non-abelian gauge theories can have this property of asymptotic freedom. And they say this in the abstract: no renormalizable field theory without non-abelian gauge fields can be asymptotically free. In particular, what they're saying is that scalar field theory cannot be asymptotically free. What I want to point out to you is something that is extremely controversial, but I want to point to you that there is a loophole in these proofs, the proofs of asymptotic freedom by Coleman and Gross, and the proof of quantum triviality by Eisenman and Duminil-Copin. And the curious thing is, that's the same loophole in both of these proofs. The loophole that I want to exploit is that both of these proofs assume that the coupling at the UV scale, so somewhere at high energy, is positive definite. Now, why do I think about these proofs and these concepts here? I started this talk by telling you about this mathematical method, the large N expansion for scalar field theory. Now let me talk to you about what happens if you apply this without any prejudice to 4-dimensional scalar field theory. You do the same thing, the same steps as in lower dimensions, and we checked that the math was agreeing with other non-perturbative methods. The main difference in 4 dimensions with respect to lower dimensions is that you do need to renormalize the coupling. This does not happen in lower dimensions, and this is specific to 4-dimensional quantum field theory. It turns out that you can renormalize the theory non-perturbatively. This has been known for a long time. There's a nice article by Parisi dating back to 1975. And what you find in the large N expansion is a fairly simple result. It says that the Baire coupling constant, or the inverse of the Baire coupling constant, is the inverse of the running coupling minus this divergence here. And you can see from the form of this renormalization condition that it's non-perturbative because it renormalizes 1 over the coupling rather than the usual perturbative coupling renormalization. And this form is exact to Lie-Ingoldt and large N, but you can also calculate 1 over N corrections The form is different, but sort of it's not conceptually different from the leading order large N result. So once you have this randomization, the point I need to emphasize again is that since you're doing this large N expansion, you're not doing a weak coupling approach. Okay, so whatever you do is maybe limited to a large number of scalars, but it's not limited to weak coupling. And that's important because normally in perturbation theory, whenever the coupling gets large, you can't use perturbation theory, so your method fails. Here in the large N expansion, that's not the case. You can do any coupling you want as long as the number of scalars you deal with is sufficiently large. Using that, you can actually get the exact running coupling in the leading order large N expansion. It's sort of given by this formula here. And there are two interesting features about this. The first thing is that if you write this down, there is an emergent scale, lambda ms bar, which you know about if you do perturbation theory too, but it's just not part of the original Lagrangian. It's kind of is something that pops up via a process known as dimensional transmutation, and this is just a feature of solving this quantum field theory. The other thing I wanted to point out is that this is a solution of large N theory in the continuum limit. Okay, so you don't have any lattice here. It's continuum. And if you look at this result here, you find that lambda r is not zero. Okay, so immediately there, this contradicts this proof of quantum triviality, which says that scalars have to have vanishing coupling constant once you go to the continuum. The other thing I want to point out is that if you look at this running coupling here, and you go to the large energy limit, so the mu is very, very large, then the argument of the logarithm is small. You take the logarithm of a small number, you get a very large negative number. And then if you divide this by a large number, you get a small negative lambda in the high energy limit. So that means that the coupling is extremely small at high energy, which is nothing else but the property of asymptotic freedom. I told you that there are two proofs about quantum duality and asymptotic freedom, both saying that this cannot happen for quantum field theories. But I want to point out to you that both of these proofs have a loophole, and the loophole is that they assumed positive definite coupling in the UV. Now, if you look at this running coupling here that you get from the math of the large N model, you find that this running coupling does go to zero in the large energy limit, but it approaches zero from below, not from above. So the large energy limit of the running coupling is negative, and that's sufficient to avoid all of these proofs, so-called proofs of quantum triviality and asymptotic freedom in scalar field theories in 4 dimensions. Here's a plot of the running coupling. So for low energies, you have the same behavior that you have seen in textbooks many, many times. If you use perturbation theory, you have to stop your analysis at some point where your running coupling gets large because you used a large, you used a small coupling expansion which breaks down somewhere here. But the point I'm again emphasizing is that if you use a large N expansion, you're not limited to the small coupling regime. This is sort of the leading large N result for your running coupling, and this whole sort of running coupling behavior in principle sort of should be taken as physically indicative, including the fact that there is this point where the coupling diverges, comes down from minus infinity, and approaches zero from below as you approach high energies. Now, if you see a coupling plot like this, the sort of standard knee-jerk reaction of high energy theories is that, oh, this part here where the coupling is negative doesn't make any sense, the theory is unphysical, this cannot happen because yeah, we don't do negative couplings. I want to point out to you that there are theories that you can probe experimentally where something like this happens too. In particular, I want to highlight the properties of non-relativistic fermions in 4 dimensions, where the coupling constant, or the role of the coupling constant, is played by the scattering length, A. And if you look at the plot, which is a theory plot but corresponds to what's done in the experiment, you can tune the coupling in experiment, or also in theory, by changing the magnetic field that these sort of non-relativistic fermions feel. And if you sort of engineer it cleverly, there's one point here known as a Feshbach resonance, H0, where the coupling actually diverges, crosses sign, and comes back from minus infinity. This is the behavior of the scattering length or the coupling constant for non-realistic fermions, which is seen in the experiment. And there's nothing bad happening when the coupling crosses sign. In fact, there's not even a phase transition between these two positive and negative coupling behaviors. It is only a crossover between the so-called BEC and BCS regime. And in particular, nothing bad happens at the point where the coupling diverges, which is called the unitary Fermi gas regime. So I want to sort of take this as a cautionary tale that maybe this notion that the running coupling behavior for scalar field theory that I've shown in this plot here is actually perfectly physically acceptable, maybe not from a sort of 1950s or 1920s classical point of view, but you need to sort of see it through the lens of quantum mechanics. Okay, now let me sort of quickly sort of summarize what's happening with this large N expansion for 4 dimensions. The large N expansion is not limited to small lambda. We've established this, and in fact, this can be tested in lower dimensions, as I sort of said before. The large N expansion is systematically improvable, and you can do quantitative checks in lower dimensions that this actually gives quantitatively good results. For 4 dimensions, applying exactly the same math, you find that there is a theory prediction, large N theory prediction, that says that scalar quantum field theory is non-trivial and asymptotically free. The point that I will emphasize here is that there are no conjectures here. There's not ADS-CFD or anything like this. There are no assumptions here. It's just math. Okay. Of course, this contradicts decades of traditional high-energy physics beliefs, which is mostly based around free field theory. And the reason is that it does not use perturbation theory. It uses a different non-perturbative expansion scheme, which again, as I want to point out, is well motivated and systematically improvable. So the question that I've been trying to answer for the past year or so is whether any of this sort of mathy stuff is actually relevant for experiment, which is what I want to talk about in the last part of my talk. So what I want to focus on is an sort of application of this math to the abelian Higgs model, again in the large N version. And again, I will be sort of too brief to sort of explain much of the details. So if you want to read more, there's a reference that I put out here from this May, which is entitled Math from Nothing. And this is the first part where we talk about the abelian Higgs model. Before I sort of talk about what we did, let me remind you about the standard version of the abelian Higgs model. Okay? So in the standard version of the abelian Higgs model, you write down a theory action that consists of a complex scalar phi coupled to a U1 gauge field with a Maxwell field strength tensor F mu nu, and a potential V of phi, which has this form here, which sort of has this tachyonic term, tachyonic mass term minus mu squared, and then a quartic potential to stabilize the field on tree-level diagrams. So the theory is gauge invariant. You can show this by checking that if you do a gauge transformation in both the gauge field and the scalar field, that the action remains invariant. You can do perturbative expansion around the tree-level minimum. So you sort of say that, okay, phi is some constant background field phi bar plus fluctuations. And this gives you the Higgs mass, so the mass of the scalar in terms of mu. The vector also gets a mass. It's given by this result here. And the expectation value for the complex scalar field is also given in terms of this mu here. Okay, so this is tree-level perturbative quantum field theory. Now I want to point out there are some problems with the standard version of the abelian Higgs model. The first problem, which is maybe only a problem in sort of communication, but nevertheless is a problem, is that if you have a gauge symmetry, in particular local symmetry, as I said continuous, but it's a local symmetry, then this symmetry cannot be spontaneously broken. Okay, so you can show this. It's a theorem. It's called Elitz theorem. So what this means is that there cannot be possibly and non-vanishing vacuum expectation value for the scalar phi. So this result here contradicts the theorem. And of course it does so because you sort of, when you do the calculation in perturbation theory, you explicitly break gauge invariance to get to this. But the point is that this cannot actually happen in any real physical system, okay? Because gauge symmetry protects this, and you know this, okay? So if you have a scalar phi that is rotating under gauge transformations, if you calculate the expectation value of a gauge-dependent quantity, the only thing you can get is 0. Okay, it's impossible to get something non-zero. Yet in textbooks after textbooks after textbooks of electroweak theory, there is this talk about the non-vanishing vacuum expectation value. So these two things just don't jive with each other. This just cannot work out in the way that we tell this story. Okay. This is not the only problem. There's another problem, which is that we start out with a tachyonic potential for the Higgs. We don't have a single example in physics where this sort of potential is tachyonic. Right? This is very strange potential. Where does this come from? What's the justification for putting in a negative mass term in this potential? I think this is a problem. There's another problem, which is that this treatment that I sort of highlighted, this was tree level. So this tree level is essentially classical. If you include fluctuations, so radiative corrections, then you find that this Higgs mass receives large radiative corrections. So basically, if you cut off the theory in sort of this spirit of putting the theory in a lattice and having your V cut off at the Planck scale and so on and so forth, you find that your Higgs mass would actually get very, very large, so on the order of Planck mass. Yet from experiment, we sort of expect the Higgs mass to be much, much less than the Planck mass. So these two differences in scales, the Planck mass from the radiative corrections and the Higgs mass at the electroweak scale, are very different. And this is known as the hierarchy problem in electroweak theory. And finally, let me point out the fourth problem, which is that if you don't use this version, but use the full version of the Higgs model, including non-abelian gauge fields and fermions and all sort of this stuff, you do perturbative evaluations of this to next to leading order, you find that this Higgs vacuum that this is expanding around is unstable. Okay, so the data tells you that whatever you're trying to fit to is not a stable vacuum. There should be a different vacuum which is preferred. So people sort of say that, oh yeah, this is possible that the universe lives in a metastable vacuum and so on and so forth. This doesn't make any sense because usually we think about cosmology in the terms of the early universe was a much hotter place. If you have a much hotter place, then fluctuations are much, much bigger. So as you cool down from this much hotter, or if you have a much hotter universe, then these larger fluctuations would explore these different vacua. So there's essentially zero chance that as you cool down the universe, that you don't get into the stable vacuum, but get trapped in this metastable vacuum. There's sort of no plausible physics argument, except if you sort of say that, oh, there's supersymmetry that prevents you from sort of going to this non-perturbative vacuum. But in the standard model, I don't see any logical reason that we can be trapped in this unstable vacuum, which is a problem, I think. So I point out this problem because I really want to point out that there's something fishy going on with the standard model of particle physics. Okay, it may only be in the communication, but even that is fishy. If we sort of go out and tell the general public there is a vacuum expectation value for the Higgs field, and we know that it's prohibited by a theorem, elliptical theorem, I think this is a problem, and I think we should be doing better than that. So in my last few minutes, let me sort of give you a very, very rapid flash of what happens if you solve this same model, the abelian Higgs model, but in the large N version, not in perturbation theory. To do this, you have to set up the large N version of this, which is kind of a little bit contrived. So instead of having one complex scalar, you start with n complex scalars. But because you don't want to have two n degrees of freedom, only one n degrees of freedom, you want to sort of have these scalars to be phase locked. Anyways, after the dust settles, you come up with this sort of theory here, where you can use 1 over n expansions to solve this theory non-perturbatively. The point I want to emphasize is that in this version, there is no tachyonic potential. There's just this quartic term here, but the coupling lambda will be running because of radiative corrections. So if you solve this model, you find that this model, even though it doesn't have a tachyonic mass term, it does give a Higgs mass and a gauge boson mass via a mechanism that's known as the Coleman-Weinberg mechanism. And the difference is that in Coleman-Weinberg, they tried to do this for the single component complex scalar field, and they threw away terms that were not under perturbative control. If you do it in the large N expansion, it tells you exactly which terms to keep at which order in large N, and you find the same qualitative feature than in Coleman-Weinberg, but the quantitative number is much nicer. It's not exactly what you expect from experiment, but it's within a factor of 2 or so. The feature of this model is that while it has no tachyonic potential, so there is one less parameter than in the standard abelian Higgs model because we don't need it. There is no scalar VAF. Okay, so you calculate phi vector and you find that it's 0. The radiative corrections are the ones that give rise to the Higgs mass. So because the sort of theory doesn't have a cutoff, there is no way that the Planck mass enters in this scenario. So basically, there's no hierarchy problem in this setup. And I want to emphasize that it's not a solution of the hierarchy problem. It's just that the hierarchy problem never enters because you never had a cutoff scale. There are 2 saddle points. One is the perturbative saddle, which is unstable, as is also the case for the standard model perturbative Higgs vacuum. But there's also a non-perturbative saddle, which you can identify in the von Weyden expansion. And this non-perturbative saddle is unconditionally stable at large N. It also predicts additional particles. So I talked to you about this auxiliary field zeta and that it might correspond to a real field. In this case, you can sort of point out what it is. It's a Higgs-Higgs bound state, and you can calculate its mass. And what this would mean is that it would correspond to a new standard model particle, which in principle is within the reach of collider experiments such as the LHC. Right now, in the large N expansion, we only have estimates for the mass of this particle, but not its width. But we want to sort of get there and sort of make a real prediction for people at the LHC to actually be able to look in data and see whether or not this predicted particle is there or not. With this, I want to sort of summarize. I talked about this under quotes new large N framework, which lets you actually solve in the honest to God sense scalar and fermionic theories in a non-perturbative fashion. The way to do this is in terms of these additional auxiliary fields, which in the case of fermions have physical interpretation, such as the zero mode being the Bose-Einstein condensate or BEC, and the fluctuations corresponding to Cooper pairs. The large N method doesn't use any conjectures. It just uses plain old math, and you can check the math in the cases where you're in less than 4 dimensions where other non-perturbative methods are available. If you just apply the methods as advertised to 4 dimensions, the large N technique, the math, contradicts the traditional beliefs. In particular, it contradicts the famous proofs based on weak coupling wisdom. And what you find instead is that in the large N limit, scalars in 4 dimensions are non-trivial and asymptotically free. And the key loophole that the large N math exploits, so it's not like by design, it just pops out from the math, is that it predicts the running coupling to approach 0 from below in the high energy limit. You might object that this means that the high energy potential is upside down, it's unbounded below, and this is true. However, we know from quantum mechanics that these upside down potentials can have sort of stable and stable bound states and well-behaved spectra and unitary quantum mechanics behavior by decades of work on so-called T-symmetric quantum mechanics, and I advertise the really sort of very beautiful work by Carl Bender on this topic. If you apply this large N math to a abelian Higgs model, it solves several problems that the perturbative Higgs mechanism has. So for instance, it solves the problem with having no VAF, guaranteeing stability or consistency with Elitzer's theorem, and it gives you the stable vacuum rather than the unstable vacuum. And there's a way that you can actually check experimentally, potentially, whether this large N expansion is the right one, which is that the large N Higgs model has additional particles, in particular the 6x bound state, which in principle can be found using available experimental data from high energy collisions. With that, I want to sort of end, and I would be happy to sort of take any questions if you have any. Thank you so much.
Okay, thank you for the nice talk. Any question from the audience? Please unmute yourself and ask.
I have a question.
Yes.
Yes.
Hi, Paul. Thanks for a very nice talk. I really enjoyed it. I was wondering, so how large the N should be to get a good approximation? Does that depend on lambda?
No. So the large N, well, okay. So the large N expansion, okay. So these are two different questions. Okay. So first of all, you can ask whether does there have to be N sufficiently large for this method to be qualitatively correct? Okay. It could be that if you take scalar field theories with finite N, let's say N is 4, 6, or 10, or whatever, that the behavior of the large N phase and the behavior of the low N phase is separated by some phase transition. And then it could be that whatever we are calculating is like in the high N phase and maybe it doesn't actually connect to the low N phase. This is possible. Right now, we don't see any indication of that. So we sort of look at 1ON expansion and sort of try to see whether sort of there's any indication of a breakdown there, but it's not something you can rule out. The one way to test this would be if you have sort of the large N result for some observable, and you do some non-perturbative solution for finite N, and you see whether these two actually sort of agree with each other or not. In 4 dimensions, this is hard to do. But we know that in low dimensions, there's no such thing. So the large N expansion just goes all the way down to N is few. It just becomes quantitatively worse as you go to smaller N.
Okay.
For 4 dimensions, we don't know. And if you could do like a lattice simulation of this negative coupling theory, you could check. But right now, this has it has a strong sign problem. It's very hard to sort of check this. So in 4 dimensions, we don't know. Of course, one thing that we can say is that we do this expansion around N is infinity, so you might always be worried about, even if there's no disconnect between the large N and small N phases, that how good are these numbers that you get from the large N expansion. And again, this is something that we don't know, but that is testable by calculating 1ON corrections and seeing how large the sort of difference is between the different orders. Again, in low dimensions, you can check this, and even down to N is 1, the leading order large N is typically off by 30%, the next to leading order by 10%, and the next to leading order by 5%. Whether this holds for 4 dimensions, we don't know.
Okay.
So